Chemistry, we're continuing on in the Foundations unit, and we're going to talk about two experimental techniques that they definitely test on the AP exam. So we'll talk about those, and you'll do a couple of assignments related to these two experimental techniques. Okay, so mass spectrometry is a way of determining the mass of an isotope. So remember that fundamental fact that this has to do with isotopes. That is, atoms of the same element but with different numbers of neutrons. And because they have different numbers of neutrons, they have different masses or weights. So it works on the principle that a lighter atom can turn faster than a heavier atom. So there you see a truck and a motorcycle. So if a truck and a motorcycle turn a corner, the lighter motorcycle will turn quicker than the heavier truck. So lighter isotope atoms curve quicker than heavier ones. And we're going to view a video reading a mass spectrometry graph, and that's one of the things they're going to ask you, they would ask you on the AP, is to be able to interpret a graph of mass spectrometry. So here's a diagram of a mass spectrometer. So it's a way of determining the mass of the isotope, and it works like this. One, the isotope atom is ionized so that it has a charge. In order for it to be moved by magnets, it has to have a charge to it. So an electrically neutral atom, one with the same number of protons as electrons, will not have a charge to it, and therefore it will not move in magnets. So you need to ionize it. You need to either add or subtract some electrons. Then two, the magnet moves the isotope through a tube. So those two, where it says ions accelerated, those are basically magnetic plates, and what they're going to do is cause the ion to move through them. They're magnetized in a way that will cause the ions to move. So a magnetic field moves ionized isotope atoms through the tube. So they're moving from left to right as you're looking at this. And then three, the isotope atom passes through a perpendicular magnetic field that causes the isotope to curve. So this perpendicular magnet causes the isotopes to curve. So it's either pushing them or pulling them, and it's causing them to curve downward down that tube. How much the isotope atom curves depends on its mass. Heavier isotopes will take longer to curve, just like the heavy truck, and lighter will take less time to curve, just like the motorcycle. So heavier isotope curves least. So the heavier isotope will hit that detector that you see there at the very end of the tube. The heavier isotope will hit towards the top of that because it can't curve as fast or as much. And that will be the line down there on the right hand side. Now the M to Z means mass to charge. So we're assuming that all the isotopes have the same charge. Therefore, the ones that are heavier will curve the slowest, and the ones that are lighter will curve the fastest. So that's what M to Z is, mass to charge. And depending on how many isotopes of a particular type, the line will get higher and higher. So you can see that the isotope number 98 is the most prevalent or the most abundant. And so the different isotopes are 92, 94, 96. Looks like there's one at 97, 98, and 100. It doesn't say what this element is. It doesn't really matter. The lighter isotope curves the most. So it goes through that magnet, that perpendicular magnet, and it can turn faster. It's like the motorcycle. It can turn faster. So it's going to hit the bottom of the detector, and it will show up on the left side of the graph. So 92 is lighter, is the lightest of all those isotopes. So that's how mass spectrometry works. Okay, now we're going to look at photoelectron spectroscopy. By the way, the differences between the word spectroscopy and spectrometry are kind of trivial, and we're not going to worry about it. You can almost use either word in either situation here. So photoelectron spectroscopy, which is abbreviated PES, is a way to determine the ionization energy of an electron. The ionization energy is equal to the energy of the photon minus the energy required to make the electron travel a distance. So let's just take an example, and that'll make this a little bit clearer. So here it looks like, again, we have a lithium atom, 3 protons, 3 electrons, with 1 in the second orbital. So a photon is a standard packet of energy delivered by light, and we'll talk about photons and light in later lessons. ionization energy must equal the binding energy that the electron is being held by the atom. So that outside electron, that second orbital electron, is being held by a certain amount of energy by that atom. So the ionization energy has to be equal to that energy that the electron is being held by the atom in order to knock it out of the atom and to ionize the atom. So the following formula gives the binding or ionization energy. They're the same number, just opposite sign. So the ionization energy is equal to the energy of the photon minus the kinetic energy of the traveling electron. So let's explain what that means. The ionization energy is how much energy it takes to pull that electron away, not to make it travel any distance away from the atom, but just to get it out, to get it unattached from that atom. The energy in the photon is the energy being brought in that's going to knock that electron out. And the kinetic energy is the amount of energy can be measured by how fast and how far that electron travels. And they have a way to do that. They have techniques for doing that. So let's just use a couple of simple number examples to see how this works. So there's electron number 1. That's the valence electron in lithium. So let's say a photon with 20 joules strikes that electron. Now let's say it causes that electron to fly out, and they're able with their instrumentation to measure that the kinetic energy is 15 joules. And that's required to make the electron number 1, that electron, travel that far. So again, there we go, same situation. There's the 15 joules. There goes the electron, it flies out there, and they measure that that has 15 joules of energy. So there was 20 joules of the photon minus the 15 joules of the kinetic energy. So the difference between those two numbers, what happened to the other 5 joules? Well, that's the ionization energy. That's the amount of energy that it took just to get that electron to get pulled away from the atom. Not to travel any distance, just to pull it away from the atom. So 20 joules comes in, it hits that electron. 5 of the 20 joules are required just to pull the electron away from the atom a little bit, and then the other 15 joules are what they measured that the electron had in it when it flew away from the atom. So therefore, the energy that comes in from the photon goes into 2 places. One is just to break the electron away from the atom. The second is to cause it to fly away. So they can measure the photon energy, they can measure the kinetic energy, and by taking the difference between those two numbers, then they know that the amount of energy it took to ionize, the ionization energy to break that electron away, was going to be the difference between those two numbers, which was 5 joules. So 5 joules is the ionization. It's also the binding energy of the electron. 20 joules of energy was absorbed by the valence electron, which then had enough energy to escape from the atom and fly a distance that required 15 joules of energy. This means that 5 joules of energy was needed to escape the atom. This is the ionization energy. So that's what photoelectron spectroscopy does. We'll take another example. Now that that electron is gone, we'll say 20 joules, a 20 joule photon strikes another one of the electrons there, and we'll call this one electron number 2. And let's say it travels a distance that requires 8 joules of energy. So there it goes. Alright, so what's the ionization energy of that particular electron? Well, 20 joules came in, the electron came out with 8 joules, so that's a difference of 12 joules. What happened to those 12 joules? That's the ionization energy. That's the amount of energy it took to break that electron away. That's the second ionization energy, and it's greater than the first ionization energy because that electron, the one you're seeing right there, was held more tightly to the nucleus. It didn't have any screening electrons, and it was basically held fully by those 3 protons there. So then there was 20 minus 8, which equals 12 joules of energy holding the electron to the atom. So 12 joules is the ionization, also the binding energy. Okay, so here's a summary. You want to don't lose sight of the big picture of what these techniques are doing with all the details. So mass spectrometry determines the mass and percentage of each isotope of a particular element. It tells how heavy it is and what percentage of the total isotopes are at that particular mass. So it has to do with isotopes. Photoelectron spectroscopy determines the ionization energies of a particular element. Okay, so mass spectrometry has to do with isotopes, that is different numbers of neutrons. And photoelectron spectroscopy has to do with ions, that is removing electrons from an atom. And that takes care of this lesson on these two techniques. You'll be given a couple of assignments that will help you to reinforce these techniques.